Welcome to the Are You GCSE Physics Ready playlist. This playlist is packed with example questions and guided solutions for every GCSE Physics topic. So it's the perfect tool to help you test your understanding. If you feel like you might need a quick review of this topic before having a go at the questions, or you would just like the ideal revision companion for these videos, then do make sure to download my free GCSE Physics revision notes, linked in the description below. If you're ready, let's dive in. So this question is about sound waves, and it says thunder is heard 30 seconds after lightning. How far away is the thunder? How would this be in a vacuum? Okay. So first thing to do is to know that I'm using my equation speed is equal to distance over time, because I'm trying to find out how far away it is, or the distance, and I've been given the time 30. So then I need to think about what's actually happening. So you see the lightning and then you hear the thunder. So you need to recognise that light travels so much faster than sound. In fact, it's so much faster that the delay in actually seeing the lightning from where it is I can take to be negligible. So the delay is hearing it travelling the sound wave all that distance to my ears in order for me to be able to hear it. So I need to know what is the speed that sound waves travel in air. And I should know that that is roughly 330 meters per second. So good, I've got my speed, I've got my time to rearrange my equation, so to make that my distance d is equal to speed multiplied by time is 330, multiplied by 30 is 9,900 meters. And the second part of the question was, how would this be in a vacuum? And the answer is, it's a slightly trick question because sound can't travel in a vacuum, so I wouldn't ever be able to hear the thunder, only see it. Okay, in this question we have ultrasound with a speed 1000 meters per second being sent down a metal pipe with a suspected crack in the pipe. The length of the pipe is 100 meters. Ultrasound is received back after 0.12 seconds. Is there a crack in the pipe? Okay, so to determine whether there is a crack in the pipe or not, I'm first going to draw a picture of the actual pipe. So it was 100 meters long, and I'm basically going to make the assumption, well, when would I have heard or received that ultrasound back if there were no crack in the pipe? So if there had been no crack, then my speed is equal to distance over time. My speed has been given me in my question is 1000 meters per second, and my distance is all the way to the end of the pipe and back to be receiving that ultrasound. So it's not just 100 meters, it's actually 200 meters there and back. So the time it would take to send my ultrasound to the end of the pipe and back would be distance divided by speed. 200 divided by 1000 is 0.2 seconds. In my question, I was told that I actually received this ultrasound after 0.12 seconds. So since 0.12 is a shorter amount of time than 0.2, I know that that ultrasound must have been reflected back at some point before the end of the pipe. And that suggests that there is a crack inside my pipe. Okay, there's a little bubble of air somewhere which is providing that partial reflection for my ultrasound wave. Okay, so the second part of this question is, a second wave is received at 0.15 seconds. How long is the crack? So, okay, let me draw the picture that we have got out here. Okay, so the left-hand side of this picture is where I'm sending this pulse from. The very right-hand side is the end of this pipe, and then I'm imagining that little rectangle in the middle, that is my crack. So, we have that green arrow to the first boundary between metal and air, the first part of the crack, and then back, and then that orange arrow is going all the way down to the second boundary, okay, which is where I've got my air into metal again, and then back to my end of my pipe again. Okay, so that's my picture. So basically what I need to notice is that this difference in my distances that my green one has travelled there and that my orange one has travelled there would actually be the length of my crack. So D, the first one, the distance that my green line travels, is the speed, which was the 1000, multiplied by the time, which is 0.12, and that gives me 120 meters. And you might be thinking, well, that's not possible because the pipe itself was only 100 meters long. But remember, that's for my green line to go all the way to the first part of that crack and then all the way back to the start of the pipe. So actually I need to divide that by 2 to get the distance from the end of the pipe to the first part of the crack. Okay, then my second one is 1000 times 0.15. My time is equal to 150. So that's the distance that orange has travelled all the way to the end of the crack and then all the way back. So if I divide that distance by 2, that gives me 75 meters from the end of the crack to the beginning of the pipe. Okay, so then I'm looking for that difference in those two distances. So 75 minus 60 is 15 meters for the size or the length of that crack. Okay, we have a submarine sending an ultrasound pulse down to the bottom of the ocean to assess how deep the submarine is. And it's telling me that the total depth of the ocean is 2.7 kilometers. Pulse travels at 15,000 meters per second and returns to the ship in 2.5 seconds. How deep is the submarine below the ocean surface? A lot of information going on there. Let me draw a diagram first. So that horizontal line is the surface of my water. I know right down to the bottom is that 2.7 meters. That coloured in rectangle, coloured in black, is my submarine. And that is some distance from the bottom of my ocean. So, okay, what equation am I using for these echoes? Well, I'm using speed is equal to distance divided by time, and I'm looking for that question mark distance between the submarine and the bottom of the ocean. So really I need to rearrange that equation so I can have distance is speed multiplied by time. Okay. It's given me my speed as 1,500 meters per second, and it's given me the total time to send the pulse there and back as 2.5 seconds. So the total distance that the pulse travels is that speed multiplied by the time, 3,750 meters. However, that is to go all the way there and all the way back to my submarine. So actually the distance between my submarine and the bottom of the ocean should be half of that, 1,875 meters, which is 1.875 kilometers. Okay, but I didn't want that. I actually wanted to know how deep is the submarine below the ocean surface. To define that distance, I need to take the total depth of the ocean minus how far the submarine is from the bottom of the ocean, and that gives me 0.825 kilometers or 825 meters. Okay, first question here, what are the main differences between light and sound waves? Okay, good. So the first most obvious one maybe is the speed that they travel. Light travels much quicker than sound. But then, interestingly, if I'm thinking about light and sound moving through different materials, and I'm thinking about going from a material like, for example, glass, which is more dense, to air, which is less dense, then my sound actually travels faster in the more dense stuff, whereas light travels slower in the more dense stuff. Next obvious difference is that light does not need a medium to travel through, which means that light can travel in a vacuum, like in space, whereas sound requires a medium, so sound can't travel in a vacuum. And then transverse versus longitudinal. My light is transverse, where the vibrations are perpendicular to the direction of travel, and sound is longitudinal, where the vibrations are parallel to my direction of travel for my wave. Okay, how would a louder sound compare to a quiet one in terms of compressions and rarefactions? So you would basically have larger pressure differences between your compressions and rarefactions, so you would have larger amplitude vibrations. Okay, explain why P waves produce shadow zones despite being able to travel through liquids. Okay, so this is a good question because, for example, when we're talking about the internal structure of our Earth, we can talk about the shadow zones on the other side of our Earth from where an earthquake took place. And then we can use the idea that S waves can't travel through liquid to describe that shadow zone at the bottom of our Earth and say, okay, well, that must be because the core is partially liquid. So how can P waves actually produce any shadow zones when they can travel through liquids and solids? Okay, so it's not like they can't make it through the liquid to the other side of the Earth. And the answer is kinks, sharp changes in their direction as they travel through the Earth. And the reason for that is because even though they can travel through the liquids, because they're going from a solid to a liquid, two different materials with different densities, you will get some sharp refraction happening in those different materials, causing those kinks. Okay, an earthquake goes off at point A. Explain where you would have to stand so that only P waves are detected. So you have to appreciate that in order for just P waves to be detected, that means that you don't have any S waves detected, and S waves cannot travel through liquids. So if you're at D, which is shadowed by the lake, then you won't get any S waves there, but you will get some P waves there. Okay, suggest why elephants can hear infrasound but humans can't. So this goes back to why a sound's allowed to propagate through certain materials and what's restricting our ears as to the types of sounds that we can hear, and that is an object's SSS, 3 S's, their size, their shape and their structure. So elephants obviously have different sized ears to humans, and they are going to be a slightly different shape and different structure as well. So their eardrums and all the bones within their ears will vibrate differently to human ears. So they can hear different or lower sounds than humans are able to hear. Baby scan gel has a similar property to a mother's skin. Use partial reflection to explain why the gel is applied before a scan. Okay, so the first thing to note is that partial reflection happens when you are at a boundary between two different materials. So in order to have a noticeable partial reflection, in other words, a wave bouncing back, then you have to have two different materials. The reason that you might want your mother's skin to have a similar property to the baby scan gel and therefore be similar materials in terms of partial reflection is then you can't get much partial reflection, and that is going to be a good thing because we need the ultrasound to actually make it through the mother's skin and mostly travel towards the baby. Okay, so it's no good having loads of partial reflection just at the surface of the mother's skin. X-rays also partially reflect, suggests why ultrasound is preferable to X-rays when doing a baby scan. Okay, so the most obvious thing is obviously the danger of X-rays. So X-rays are more dangerous. Why? Because they are higher energy waves, and there's more on that in the later topics. Just before we go into the tips and tricks section, if you do want some extra advice to getting that grade 9 for your GCSE, then why not download my free 20-minute exam success guide? Just click on the link in the description below. I'm going to give away all of my best advice and secrets, and completely for free, so why not? Okay, tips and tricks for this section. So first one, distances and reflections. Be careful, if you just use the speed and the time, that will give you the distance to travel there and travel back. So you need to know whether you want that total distance, or actually, do you just want the distance between the thing and the thing that it was reflecting off? Okay, so just make sure that you remember that the distance you actually get could be 2 times the distance you're looking for. S and P waves, just a quick way to remember which way round they are. The S looks like a transverse wave. So imagine it, so you can remember that those are transverse and therefore the P ones must be the longitudinal ones. And S stands for solid, i.e. solid only. So P waves, solids and liquids can travel through P waves, but only S waves can only travel through solids. Light and sound, be careful in a question, just to be careful about what will happen to the speed of light and the speed of sound depending on the materials that it travels through. More dense stuff, your sound travels faster, but your light travels slower. Just to have in the back of your mind that sound travels at 330 meters per second in air as a sense check. So if you get any kind of sound wave and it's traveling faster than that, but it's in a solid material, then that makes sense. But if you get something that's traveling slower than that in a solid material, then you might want to think, okay, have you done part of your calculations wrong? So it's just as a helpful check for your answers.